Okay, so I'm back now. So we're talking earlier about the bromination reaction of our alkanes, no? And we learned that bromination is more selective than chlorination reactions. And if you want to predict on the kind of the percentage of the product of the alkyl halides that we produce, now we look at on the kind of the radical that's actually produced in the process, no? And we've learned that a 3-degree radical is more stable than the 2-degree radical than the 1-degree radical. So here, if you look at the mechanism, if you go back again to the mechanism of the reaction, for the halogenation reactions, of course, remember that the first step is the dissociation to form your Br dot, no? 2 moles of your Br dot. Of course, you have an unshared electrons. Once you have your Br dot, it will actually react with your alkyl halides. You have your CH3, and you have your CH3. Of course, the other one is hydrogen. Okay, remember? And so, of course, ano siya, nung ka-unshared, no? But you have an unshared electron here. And of course, to do that one, there will be a homolytic bond cleavage here. One will go one arrow here, and the other one will go there. Okay, one side now. So what we actually obtain is CH3, C, CH3, CH3, and you have your dot. Of course, you have your dot plus your HBr. No, you will form by homolytic bond formation. You have your HBr. Of course, you have your that there, and you have your radical here. You will form with another Br dot. Okay, you have just copy this one. So what we actually formed is a 3-degree. You have a 3-degree. You have a 3-degree radical here. Okay, 3-degree radical. And in the process of forming, what you obtain, okay, you will have your dot, Br dot, and you actually produce your alkyl halide. Okay, asan po? So you actually have your Br dot there for the termination step. Alternatively, you can also have your Br2, your BR to actually form your CH3, C. Again, you will have your homolytic bond cleavage. This is just another propagation step. You will have your kani, red. Okay, there will be homolytic one electron will go to bromine, the other will go to the other one. So you will have your Br and plus Br dot. Or we can, pag Br dot, just remember na panay unshared. 7 lang siya. Okay, and you have your Br radical. Alternatively, you have the termination step. You will have this. Let's just copy this one. Okay, and plus you will have your plus your Br dot. Okay, you will form your kanipot. No? This is already your termination step. So what I'm trying to show here is we don't forget now that in the process, that in the process of forming our alkyl halide, we always have to consider the kind of radical that we produce during the reaction. So here again, you have a 3-degree radical, which is much more stable as than if we form a 1-degree radical. So this one is our product. Okay. This is one of the termination step. Of course, the other termination step is this one will have to react with another radical, no? But if it reacts with another alkyl halogen radical, like Br dot, no, you have this one, your kind of product, which is a 3-degree alkyl halide. So if you want to produce our kaning isa, no, the radical that will be produced is a 1 degree radical kaning dili. So we can have this. If you have, okay, you have this one, you will have your, let's copy this. CH3, you have your CH3, CH3, is hard hydrogen. So I'm going to emphasize on the red. So emphasize on the hydrogen that will be abstracted. No? So you will have your, you will get your, of course, your CH3, CH3, and you will have your CH2, and then you have your dot, and then you have your hydrogen here. So this one is plus your, sorry, will be abstracted with your Br here, like your Br dot. You have your Br dot. Okay, so this one will be abstracted. So one will go to the hydrogen and the other will go to the CH2. And again, you have here your HBr, right? So this one, I would like to emphasize here that what you get here is a 1 degree radical. What you get earlier here is actually like, it's actually a 3 degree radical. So between 3 degree and 1 degree radical, it is much more stable. The 3 degree radical is much more stable, and that is the reason we obtain a greater proportion, a greater yield, no, for a tertiary alkyl halide. Okay, I hope that's able to follow. So if you get confused, you always have to go back to the mechanism, and of course the end product of this is your down next. So down. Okay, your end product will also, for this, of course, will be your 1 degree alkyl halide. Okay, plus your plus Br plus Br dot. Okay, first I'm gonna show you. You will get your 1 degree alkyl halide. Okay, so 1 degree. And this one is produced at the lower yield, like traces lang siya you have in here. Okay, so and this is the reason why we were able to obtain a greater amount again of our 3 degree alkyl halide. No? And this is for the bromination reaction. And you will look at on the chlorination reaction, no, its the yield is different. And here the chlorine is not selective as that of the bromine here. They're in the radical reaction. So here somewhat, no, it follows on the fraction of the halogens it's being present compared here. But in our prediction again, but it still follows for our prediction that it should have been 10% lang ang makuha nato nga alkyl halide nga kani 10% lang. But we actually obtained 63%. No? And for the reason, 90% na initial supposedly, and this one should be 10%. But we actually get a higher proportion than 10% as predicted, for reasons that the 3-degree alkyl halide, the 3-degree radical that's being formed in the process is much more stable than a 1-degree radical. So that is for the bromination. So we had the chlorination, we had the bromination, and of course, if bromination is more selective than chlorination. And what if you're gonna be using fluorine instead of bromine or chlorine? So fluorine being a smaller atom as compared to your chlorine and bromine, fluorine is actually more reactive than chlorine, no? And even less selective than chlorine. So if fluorine earlier in the reaction is much less selective, how much more for chlorine it is. No? So because the energy of activation for the abstraction of any type of hydrogen by the fluorine atom is low, there is little difference in the rate. So here in the process, when we're trying to abstract our hydrogen, how do we abstract our hydrogen? When we abstract our hydrogen here in this process, there is that energy that's being required when we dissociate our alkane here to using a homolytic bond cleavage. And the energy required to dissociate this one to produce a 3-degree radical is much less, okay, than the energy required to dissociate this hydrogen here to form a 1-degree radical. And it is for that reason, similar to that the energy of abstraction for a 3-degree is much less. To produce a 3-degree radical is much less than the energy required to produce a 1-degree radical, than the energy required to abstract your hydrogen here to produce a 1-degree radical. So this one is the energy required to abstract hydrogen here to produce a 1-degree radical actually is much higher, and it is also for that the same reason that the energy of bond dissociation is much less here as compared here, that the 3-degree radical is much more stable than the 1-degree radical. Okay, so let's go back to for the fluorination reaction, the energy of activation for the abstraction of any type of hydrogen by the fluorine atom is low. There is a very little difference in the rate of which 1 degree, 2 degree, or 3 degree. So dili klaro, no? Kung 1 degree, 2 degree, maura ang energy required to abstract the hydrogen to form the radical. So dili selective si fluorine. Pero kung makita nimo ang difference, katabi tang table that we have shown in before, like this one, like the table, no? Like this one, if you remember for our last discussion, we form here the energy required to abstract the hydrogen to form different kind of radicals. The energy to form a 3-degree radical, the energy required to break this bonds, carbon hydrogen bond in homolytic bond cleavage to form a 3-degree radical is much less as compared, this one, the icon in red. To produce your 3-degree radical is much less. You only have 400 kilojoules per mole as you compare to the bond breaking process of this one, the carbon hydrogen. To produce a 1-degree radical in blue, you require an energy which is of a larger amount, 422. And again, it is for the same reason that the production of a 3-degree radical in the halogenation process is much more selective here in the bromination process and here. In the fluorination, kaning energy niya nga difference kung 1 degree or 2 degree, dili siya klaro. So dili klaro ang energy required to produce your radical in the fluorination reaction. So therefore, dili selective si fluorination reaction. Balikta. Okay, so ano po? Okay, so this is what's being said here. Reactions of alkanes with fluorine give almost the distribution products that you expect. All the hydrogen of the alkane are equally reactive. So maura, it doesn't make sense whether 1, 2, or 3 degree. Parehara siya og energy of abstraction. So let's look at the geometry of our alkyl radical. So we have mentioned earlier that the carbocation and a radical carbon radical would have a similar geometry, and it utilizes actually the same hybrid orbital. So here is the geometry of your alkyl radical. Now you have your carbon bonded to 3 atoms, and it assumes a trigonal planar shape, no, and it utilizes an sp2 hybrid orbitals. In the carbocation, you have an unhybridized, or even for any carbon that utilizes an sp2 hybrid orbitals, no, it will have a p unhybridized orbital. So if it's a carbocation, this p unhybridized orbital would be vacant. In the case of a radical, naa siya isa ka electron nga nag-occupy sa unhybridized orbital. In the case of alkenes, no, kaning unhybridized orbital, makasilingan siya carbon pod niyan ay unhybridized p orbital, ma-overlap siya sideways, no. In the case of radical, naa siya isa ka electron that occupies the p unhybridized orbital. So it's lying up and below the plane of your carbons trigonal planar in your geometry. Now this is like this one, Canadian electron density of the radical that would be most likely found in the p unhybridized orbital. So isa rin na siya ka-electron. No? So again, sa carbocation, this p unhybridized orbital is vacant. No? So for instance, nakasilingan ni si carbon o bili ni hydrogen. This is hydrogen in the example. This is hydrogen. This is CH3 dot actually. Methyl radical, no? So for example, kani si carbon, nakasilingan siya ng isa ka carbon, no? Which would have another CH3, CH3, CH3. So kung na kay CH3, like CH, no? And it utilizes like this, for instance, kapihan. Okay, so for example, instead of hydrogen here, now I just want to illustrate what happens kung say radical, instead of hydrogen here, natay carbon. Okay, you will have a carbon here. And then the carbon is bonded to hydrogen. Maybe I use gray, like hydrogen, 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 okay? And this carbon here utilizes an sp2 hybrid orbitals, and you have, of course, your sp2. This is the p and hybridized p orbital. Okay, there is one electron occupying this unhybridized p orbital. So kung makasilingan gani siya o carbon nga na siya is CH, okay? So this carbon utilizes an sp3 hybrid orbitals. Okay, so sp3 hybrid orbitals, makasilingan gani siya. So there is, sa itsura ni sp3, murag yapon siya, like there is an S and there is a P part, right? There is an S and there is like an S like that, no, like a lobe nga in. And then it will be overlapping with the hydrogen. So murag lobe siya gihapon. It's like that, murag siya globe. And overlap sa S. So you have your sp3, and then you have your S from your hydrogen here, this hydrogen. Okay, you have your S, nagamay nga sp3. This is your sp3, and then you have your hydrogen, which would have an S orbital, an sp3. So kay sp3 man ang gigamit na orbitals niya din hiya, okay, and the angle is like 109.5. Na tanaw ni siya, it's like more siya parallel here. So what happens actually is that kaning sp3 orbitals dili between carbon and hydrogen will try to stabilize the unhybridized p orbital here because it contains only one electron. So kailangan siya paired electron. So murag na siya side, I'll use green. Murag siya na is siya overlapping, no? Sharing of electrons sa iyang adjacent nga CH bond utilizing sp3s. So there is like sharing of electrons, or ano say tawag ani, overlapping, no, of the orbitals between that one. So in such a way nga mura bitaw kung PP, if you remember, if you have your kani, if makasilingan siya another if this is carbon, for instance, and naakay unhybridized p orbitals, no? Like if you have your hydrogen, like for example here, and if this is, for example, electrons, and this is how the pi bond, remember, pi bond is being formed. There is a sideways overlap. But if you have, for example, a radical here, radical carbon here, nga containing lang only one electron, no, it can be stabilized. It can be stabilized by the overlapping or sharing of electrons adjacent niya kaning radical, no, by CH_Sp3. And you call actually this one to be katong hyperconjugation. So you don't forget the hyperconjugation effect, no? It's being utilized by a radical or a carbocation, can be always stabilized by the hyperconjugation effect. So when would that happen? Whenever there is an alkyl group or a carbon utilizing sp3 s orbital, no? It will try to stabilize this one. That's why a 3-degree radical is much more stable than a 2-degree and a 1-degree because it can be stabilized. The 3-degree is much more stabilized using the hyperconjugation effect. So imagine if daghan na siya, no, inaning a carbon being bonded to hydrogen, no, hydrogen here, and you have your sp3s. I hope na klaro akong illustration, sp3s orbital na sp3s orbital. Okay, and so therefore the 3-degree radical is much more stable than the 2-degree, 1-degree by virtue of the hyperconjugation effect. And another reason for the stabilization of your radical, another way to stabilize is, aside from the hyperconjugation, is you can have, of course, you have the hyperconjugation. The other way is hyperconjugation. Of course, the other one is electron donating inductive effect. Okay, and later we'll see in our next slides, is you have the pi electron delocalization. Okay, it's already 6 p.m. So if you can give me 15 minutes more, to proceed, to share, go back to our PowerPoint. So this is the geometry of your alkyl radical. You have the radical is occupying the unhybridized p orbital, lying up and below the plane of your carbon, no, trigonal shape of the carbon. Okay, halide. So I think it's the 10.6, no. In the next slide, so I actually wanted to finish chapter 10 before we have your sem break. Let's see how many. It's slide 50. I still have 40 slides. Approximately I will have 40 minutes now to finish 40. So ano na lang, it's already 6 p.m. And so what we can do is I'd like you to practice on the mechanism and predict. So I'm gonna upload na lang problem sets for you to work on while you'll be if wala mo lingaw no during your break. And of course I will change na lang. I will also upload the midterm exam, no, so you can practice and you will have an unlimited time to correct your mistakes, no, for that exam, no. Like of course there will be questions that you already know the answers, but tarantar lang. So I will open that exam again and you will practice in an unlimited manner so that you can correct, and I hope that the exam will become, or the quiz becomes interactive on your part, that you can correct. I'd like you to correct your mistakes for the midterm so that by the next time you encounter such kind of reactions, no, you will be more perceptive on to answer on the questions, particularly on the reactions. So since it's already 6 p.m., that ends our discussion na lang for chapter 10, no? Because masin maalanganin, and for the next part, on after your made foreman, tama. So you'll have your, hala, wait lang ha. You will have your ay 26 pa man day taron. I was thinking 29. So we will continue actually on Friday. We can finish chapter 10 on Friday. No? So we'll finish on Friday, chapter 10. And your some break, not some break, midterm break will be on May 2 to 7 plus 9. It's still holiday. So 10 din na holiday. You can have our exam, or not exam, continue with our lesson on 10. And tomorrow, if you are available, though I do not require you, so I'll find an activity for you to work on for your laboratory. And after that midterm break, then we can do more face-to-face activity in the lab. Okay, so tomorrow I still have to look for an activity you can work on for your laboratory. And for now, that ends our discussion for chapter 10, and we'll continue on April 29 to end with chapter 10. So we have 3 meetings for chapter 10. And then before we move on to another topic, next meeting. So do you have questions? And 59. 90, so that should be 40 minutes. I really hope that paspas na discussion next meeting. Okay, so again, that ends our discussion. Di na ako magpaalanganin of discuss on this reactions that generate tetrahedral chiralities on first time. The discussion might take too long to discuss. So we're gonna finish today now, and we'll continue on Friday. Okay, and then for your koan, do not forget to indicate your attendance. So that ends our discussion, and I'm gonna insert katong akong illustration ganyan if you'd like to for that. Okay, so that's all. So if you have no more questions, and also I will upload problem sets so you can work on problem sets for chapter 10. Oraton, that ends our discussions. If you have no more questions regarding your exam and so on, then oraton. Tanan na ba naka-indicate sa attendance? Niabot data og 13 karong adlaw. Okay, so wala si Mark ug si Kuan yan, no? Okay, so maura to. See you next Friday. See you on Friday. You have no more questions.
Thank you, ma'am.
Okay, bye. Mamaya na kaya itong na-discuss, no? Anyway, I will upload, no, the PowerPoint so you can study in advance.
Ma'am, pwede mag-ask po sa recording. Thank you po.
Recording also for the last time. Sige,
Yes,
sige, I
ma'am.
will try to upload later.